Determining a limiting reactant is really just one step further than the other stoichiometry problems that we've been considering. When you talk about limiting reactant, you're talking about a reactant that's going to be exhausted or used up first. And while it may be easy to say, oh, well, it's going to be the one with the least mass, that's not always the case. We have to be, first of all, we have to change to moles. And then we have to use the mole ratios in the balanced chemical equation if we're going to make a proper stoichiometric comparison. So what I've chosen to do here is to take aluminum and aluminum chloride, or sorry, and copper 2 chloride, and what we want to do is figure out which one of these, okay, which one of these two reactants is going to be the limiting reactant. So before we get going too far, we have to have a balanced chemical equation, and that would be aluminum plus copper 2 chloride. And we're going to make aluminum chloride and elemental copper. Okay, so there are products, reactants in our products, and I hope you recognize that that's a single replacement reaction. And if we were maybe doing this on our own, you'd want to check to make sure that aluminum is more reactive than copper, and it is. But we also need to make sure that we balance this. So if we've got, let's see, we've got 3 chlorines on one side, on the product side here, and 2 chlorines on the reactant side. So we can tell we're going to need to put a 3 here and a 2 there, but that also means we're going to need a 3 in front of that copper and a 2 in front of the aluminum here. Okay, so as with other stoichiometry problems, we have a balanced chemical equation to begin with. We need that. So the next step is going to be converting to moles, and we'll do that on the next slide. So for your convenience, I've recopied the values and the identities of the substances over here. We have 1.349 grams of aluminum. Okay, we have to divide by the molar mass in order to get the number of moles, and I think if you look up the molar mass of aluminum, it's 26.98154, and when we do that, we get 0.0500, using the right number of significant digits, moles of aluminum. Okay. Following a similar process down here, if we take the copper 2 chloride and divide it by its molar mass, because again we have to work in moles for stoichiometry problems, and we would have a mass of about 134 for copper 2 chloride. Anyway, when we do that, find out there's 0.009996 moles of copper 2 chloride. And again, we might be tempted at this stage to just say copper 2 chloride is the limiting reactant because it has a fewer number of moles. We can't do that, all right? We can't do that right off the bat. We have to look at how it's supposed to combine in the balanced chemical equation, which we'll do in the next slide. There are a couple of different ways to figure out mathematically the limiting reactant, but what I like to do is to pick a product. In this case, I'm going to pick the copper here, okay, and figure out which of the two reactants makes the least amount of copper. That's going to be our limiting reactant. So what we need to do is to set up a ratio or a proportion and say, okay, well, how much copper do I get for each aluminum and how much copper do I get for each copper 2 chloride? And again, this is the mole ratio, so the third step, the mole ratio. So we can see from the balanced chemical equation that I get 3 moles of copper produced for every 2 moles of aluminum that react, right? So here's the 3 that we have in the balanced chemical equation and the 2 up here. If we do that out mathematically, we should get, let's see, I'll make a little, move it down here, 0.07500 moles of copper produced. Okay, I'm just going to change colors so that we can look at the other one. For the copper 2 chloride, I guess this in some respects might be a little bit easier. We get, again, setting up the ratio here is that 3 moles of copper produced for every, we're going back up to the chemical equation here, 3 moles of copper 2 chloride that are consumed. And so we get 0.009996 moles of copper. And now we can say that indeed the copper 2 chloride is the limiting reactant. Okay, this is our little LR right here, because it makes the least copper. Okay, it's the reactant that's going to run out first. We'll exhaust our supply of copper 2 chloride of our blue-green powder before we will aluminum. Okay, let's go one step further and ask how much of the copper, how many grams of copper is actually produced, and we'll do that on the next slide. Okay, once you've identified the limiting reactant, all calculations will probably begin with that. So let's just make a note that all calcs will now begin with the limiting reactant. Okay. So we saw that in the last slide that the moles of copper 2 chloride, which are a limiting reactant, they react in a 1-to-1 ratio to produce copper. So we get the same number of moles of copper produced. If I want to figure out how many grams that is, I simply multiply by the molar mass of copper, which is 63.546 grams. That's for every 1 mole of copper. It's the molar mass. Just remember that. And I should end up with 0.06352 grams of copper produced. Okay, we can ask a few more questions that in terms of calculations. Let's try one more on the next slide. All right, let's say we wanted to know how much of the excess reactant remains. Remember that the aluminum was the excess reactant, and we had 0.0500 moles of aluminum to begin with. I put that in here for you. Okay, that's how we started. As I said in the last slide, we begin all calculations, everything we want to know, with the limiting reactant. So again, I copied that in here. And to figure out how much Al is left, we have to figure out how much was used. So we want to set up a proportion between aluminum and copper 2 chloride. If you go back a couple slides and look, you'll see that the mole ratio is 2 moles of aluminum are used for every 3 moles of copper 2 chloride that react. So if we throw that baby in our calculator, we find out that 0.006664 664 moles of aluminum are used in the reaction. So not a whole heck of a lot. To find out what's left, we'd take what we had to begin with and subtract off what we had to use, and that was what we should get left. Let's do that on another slide. We have, of course, what we started with, 0.05000 moles of aluminum at the beginning. and then we used 0.006664 moles Al used, and therefore we have 0.04334 moles of aluminum remaining. Okay, so just one other kind of calculation you can do with these limiting reactants. Let's do one more thing and look at the percent yield. We'll do that in the next slide. Alright, so if we want to calculate the percent yield, we have to be told what our actual yield is. We can't just figure that out. Let's say that I tell you that you actually get 0.04975 grams of copper when you do this experiment, okay, when you actually do it in the lab. And you'll remember from a few slides ago, what we should get is 0.06352 grams of copper. Okay, again, that's if everything goes perfectly and there's no loss of any kind along the way. Turn it into a percent, we multiply by 100, and when we do that in our calculator, our percent yield would be 78.32%. Okay, so a pretty good yield, about what we would expect in a typical high school laboratory. You know, again, maybe we lost some when we were decanting or trying to dry our product. You know, if we'd gotten more than 100%, maybe there was some contamination, but a pretty good yield all in all. Okay?